We would like now to go over further examples of integration. It seems that in the last video on integration by parts, we had said that we would have given the formula for integration by parts for the definite integral, which we never did. So let's just give it real quick. It's actually quite natural. And basically what you have to do here is take the difference between the values of this at the endpoint, and then you just have your integral. So this integration by parts for the definite integral, we're not going to go into any examples, but we're going to see some further examples of integration. And in particular, we would like to look at the case of trigonometric functions. So how can we find the derivative of cosine square of x? Okay, that's kind of interesting, and it can be done in two ways, both of which are quite remarkable. So let's start first of all with two integrations by parts. So we can think of cosine x as cosine x times cosine x, and the second cosine x, if you like, can be thought of as the derivative of sine x. The moment you have done something like that, you can start an integration by parts. So this will give you cosine x times sine x minus, and now you will have to put the prime on the other component. The derivative of cosine x is negative sine x, and that's what we get. And now what we have is, let's clean up a little, cosine x sine x minus, two minuses give us a plus, sine square of x. And now it's kind of interesting because you can think of sine square of x as 1 minus cosine square of x. That's the Pythagorean theorem, so 1 minus cosine square of x. And we're in a case that we had seen before, so this will be, can be written as the integral of 1 dx minus the integral of cosine square of x dx. And now we can transfer cosine square of x on the other side, so we will have 2 cosine square of x is equal to cosine x sine x, and the integral of 1, of course, is x. Now we have to put a plus c, and then we divide by cosine by 2, and that will give us cosine x sine x over 2 plus x over 2. And we don't need to write c over 2, we just write c, because c over 2 is as generic as c. So that's one way to do it, right? And it's a very, very interesting way to do it, but there is another one. And the other way comes from a trigonometric identity, which is that cosine of 2x is cosine square of x minus sine square of x, which can be further written as cosine square of x minus 1 minus cosine square of x. Again, this is the Pythagorean theorem. And this means it's 2 cosine square of x minus 1. And this implies that cosine square of x will be equal to cosine of 2x plus 1 over 2. So we solve for cosine square of x. And so the integral of cosine square of x dx is equal to the integral of cosine of 2x plus 1 over 2 dx. And this is going to be, I mean, you can do a substitution, or you can remember the examples that we had seen for such integrations. It's sine of 2x over 4 plus x over 2 plus c. And, you know, this is what you might think is kind of interesting, that if you look at the previous answer that we found and you compare it with what we just found, you might think to yourself, oh, they're not the same. Well, they are the same. All you need to do is take into consideration that sine of 2x is equal to 2 sine x cosine x, and then you will realize that they're indeed the same. Now, we have a sort of gap with, we know how to pretty much take the antiderivatives of all trigonometric functions, with the exception of secant and cosecant. And the question is, how do you find the derivative, the antiderivative of secant, right? So in some books, you're going to see that they suggest a crazy substitution that really doesn't make any sense unless you know what the final answer is. Let me just say that this antiderivative is simply ln of absolute value of secant x plus tangent x, which seems quite interesting. The only way to verify, one way to verify this is to actually take the derivative of ln of secant x plus tangent x and indeed see that it's equal to secant x. Let's do this real quick. I mean, it is an interesting differentiation. So take the derivative of this. In general, when you have ln of absolute value of x, the derivative is 1 over x. So this will be 1 over secant x plus tangent x by chain rule. And then you need to multiply by the derivative of secant x plus tangent x. The derivative of secant x is tangent x times secant x. And the derivative of tangent x is secant square of x. So now you can factor out the secant x from the product. So you will have 1 over secant x plus tangent x times secant x times tangent x plus secant x. And this cancels with that, giving you just secant x. And that verifies that this is really the correct antiderivative. Now, one might ask, well, how in the world does one think to do something like that? And there is a nice little way to do it, which is not that bad, but we don't want to go through all the details. It's just a good idea to show how one gets started. So remember that secant is 1 over cosine x, and we think of this as cosine x over cosine square of x. And here, what we do is we rewrite this as cosine x over 1 minus sine square of x. At this point, we do a substitution. U is equal to sine x, the u is cosine x dx. And then we get this integral. We haven't really, and it's not our goal for this particular course to discuss these integrals, but this integral is not so hard to do. Once you find this integral, which obviously is going to be reduced in to an integral of 1 minus u, 1 over 1 minus u, and 1 over 1 plus u. So you will have a couple of logarithms there. Once you go back to your x's and you work everything out, then you eventually come up with the expression that we just showed. So we're not going to show all the details because this falls under the integration of rational functions that we're not going to consider in this course. However, that's how you find the integral. It's not a good idea to leave it hanging there thinking that somebody just imagined that amazing antiderivative and it turned out to work that way. No, there's a natural way to actually find it. At this point, it might be a good idea to discuss a few higher powers. So maybe secant and tangent. So for example, if you wanted to do the antiderivative of secant to the third of x, how would you do it? Because secant square of x has a very easy antiderivative, it's tangent, right? So we did secant, we did secant, we can do secant square. How would you do secant to the third of x? And secant to the third of x is kind of interesting because in a case like this, you just go with integration by parts. So you write it as secant x times secant square of x. Now secant square of x is the derivative of tangent, and the moment you have something like this, you know that your integration by parts engine is ready to roll. So you will have secant x times tangent x minus, and now you put the prime on the other component, which will give you secant x times tangent x times tangent x. Secant x times tangent x being the derivative of secant x, of course. And once you get here, actually, it's kind of interesting because you can still write this as secant x times tangent square of x. And here there's an interesting identity that everybody should know. So if you take the Pythagorean theorem and you divide it by cosine square of x, then what you get is tangent square of x plus 1 is actually secant square of x, right? Which tells you that tangent square of x is secant square of x minus 1. So this will be secant x times tangent x minus secant x times secant square of x minus 1 dx. And of course, this will give you secant x times tangent x minus secant to the third of x dx plus secant x dx. And now everything here is workable. So it's exactly the kind of situation that you have to realize that this is now equal to that, and this appears twice, so you can bring it over to the left, and this will give you 2 secant to the third of x is actually equal to secant x times tangent x. And we already saw what this would be, ln of secant x plus tangent x plus c. And then all you need to do is divide by 2 and you're all set. And how about, then you can ask, how about powers of tangent? So the derivative of tangent x can be found, the antiderivative of tangent x can be found through a substitution. For tangent square of x now, for tangent square of x, it's pretty straightforward. We just said that tangent square of x plus 1 is secant square of x. So this will be the integral of secant square of x minus 1, which is very simple. The antiderivative of secant square of x, of course, tangent. So this will be tangent x minus x plus c. And then, of course, one can ask what happens if you have tangent to the third of x dx. And here, you can again play the same game, meaning you can write tangent x times tangent square of x. Yes, but tangent square of x is secant to the square of x minus 1 dx. So this will become tangent x secant square of x dx minus the integral of tangent x dx. And these are two interesting integrals on their own, but they're quite simple. For the first one, actually, you can do a substitution. Why? If you do u is equal to tangent x, then du is right on the plate waiting for you, right? So this will give you the integral of u, which is 1/2 u squared. So this will be 1/2 tangent square of x. And the other one, the integral of tangent x, we have already seen it. It's ln of secant x, of absolute value of secant x. So there you go. At this point, we should say that you can have situations in which it seems that you're doing the same thing over and over. This could be actually what we just saw, could be one of those situations. But let me just say that somebody gives you the integral of x squared e to the x dx. So you start by an integration by parts. You acknowledge that e to the x is the derivative of itself. And that gets you started with x squared e to the x minus the integral. So now you want to take the derivative of x squared, which is 2x e to the x dx. And at this point, you realize that what you have got is pretty much an integral of the same pattern with 1 degree less. And of course, we've already seen how to do this integral, right? That was one of the first examples of integration by parts that we saw, which was x minus e to the x plus c. So the final answer will be x squared e to the x minus 2 x e to the x plus 2 e to the x plus c. But that's not the point. The point is that you start with an integral and you get an integral that looks exactly like it with 1 degree less. And in fact, you could have done this with any power, meaning you could have started with x to the n e to the x dx, and pretty much apply the same argument. And that would have given you x and e to the x minus, and now you would have, of course, take the derivative of xn, which is n times x to the n minus 1, e to the x dx, which is the same thing as x to the n e to the x minus n times x to the n minus 1 e to the x dx. So all of a sudden, what you're getting is pretty much what we call a reduction formula that gives you this integral in terms of a very similar integral that is of 1 degree less. So in fact, by using this formula, if somebody asked you, okay, so what's the integral of x to the 10th e to the x, you would just have to apply this formula 10 times till you got down to the integral of e to the x, which of course you know it to be equal to e to the x. The bottom line is that all you would have to use is this algebraic relation, no integration. There is one only integration that is being done implicitly in deriving this formula. And after that, you can just work with pure algebra in order to find the integral. So these are called reduction formulas, or sometimes you can talk about a recursion in integration. But the bottom line is that you can use these formulas, and you can find such formulas for many types of integrals with, especially with powers, or the parameter can occur at different places. So with this, we can say that once one gets into the realm of integration, it's a very rich journey with many interesting examples, many interesting methods. And it's not like you can work with general principles. You have to look at different examples, appreciate the special nature of the examples that you see, and pretty much build on the experience that you gain while working with such examples. And that's the end of this video. Thanks for watching.